All right, we're going to work on this homework, which is limits and continuity. We went through a couple of the first few problems, but we'll start right from the beginning. The first one asked about the average velocity. And so what we'll do is we've got 1 point is 108, and another point is 188. The function s represents position, and so the average velocity is going to be s at 5 minus s at 1 all over 5 minus 1. That's 188 minus 108 over 5 minus 1. 80 over 4, 20. 20 units per unit. Number 2, you're given another position function, negative 16 t squared plus 84t. And it passes at the point 0.75, and the function evaluated at 0.75, and 3, and the function evaluated at 3. And the question is, which one is it? And it is C. The secant line is given by connecting these 2 points here. This one's not right because the point has to go, the line has to go through this point, right? And here, this is not going through 0.75, it's going through the origin. It looks like they give us the points, so that looks like that's 108 minus 54 over 3 minus 0.75. We'll have to calculate that for the slope of the secant line. So we'll get out the calculator for that. 108 minus 54, we're talking about 54 divided by 2.25. 24. What is the relationship of the slope to the moving object? The slope is the average velocity of the object over, this is the wrong interval, it's over the interval 0.75 to 3. The slope is the average velocity of the object over 0.75 to 3. There's the function f of x equal to negative 5x squared. Here, the slope of the secant lines. Here, you just need to do this plugging in. We'll do the first couple, and then I'll leave the rest to you, but we're doing f of 3 minus f of 2 all over 3 minus 2. That's the first set, so that would be f of 3 is negative 5 times 3 squared, negative 5 times 9, negative 45. F of 2 is negative 5 times 2 squared, which is negative 5 times 4, which is negative 20. And then you would do negative 45 minus negative 20. Watch the signs there. All over 3 minus 2, which is equal to negative 25 over 1. So negative 25 would go here. And then you would do the same thing for these, right? So the next one you would do f of 3 minus f of 2.5 all over 3 minus 2.5. And so there, you would just calculate what that is. F of 3, we already have. F of 2.5, you would then calculate, and then that number goes here. And then eventually, they'll want you to calculate what this number is. And so we'll do the last one just to see what the answer should be getting closer and closer to. So f of 3 minus f of 2.999 all over 3 minus 2.999. And for this, I'm going to use Desmos to do this. So negative 5x squared And so I want to do, I've assigned that function, I press the division button, f of 3 minus f of 2.999 divided by 3 minus 2.999, right? Negative 29.995. And again, the whole reason why we're doing this is that we're trying to get an approximation to the actual slope of the tangent line, and it looks like that thing is getting closer and closer to negative 30. And you'll see that. And so this is how you can also check that you're putting in the right numbers, because they should all be getting closer and closer to one number. In this case, it looks like it is going to be negative 30. Here, negative 16t squared plus 256t plus 272. Which one is that? That one in this case is C, right? So this is a parabola, and you can graph it if you like, but it's a parabola whose vertex is on the positive side of the x-axis. These are wrong because the negative 16, the a here for this quadratic is negative, so it has to be opening downwards, and the value is pretty big, so they should be a little bit higher here. If we want to zoom in, let's zoom in and see if we can calculate where this is happening. This is happening 1, 2, 3, 4, 5, 6, 7, 8. It looks like this is happening at 8, the highest value where the tangent line is 0. But this is also the value where the instantaneous velocity is 0. So the instantaneous velocity is 0 means where's the tangent line equal to 0, and it looks like it's t equals 8. And in your graph, you'll see there'll be some integer value, and I think they'll be going by ones. You just need to find out where it is. And so now we're going to get an idea that the answer is going to be 0. So again, we'll just remark that the slope here is 0. And now they want us to verify this on this table. And so again, we're just going to do the same thing we did last time and look at f of 8.5 minus f of 8 all over 8.5 minus 8. Okay, and so from what we're seeing here, when we do this, the answer to this question at the end should be 0 because the slope here is 0. And so this should be 0. And now we just need to fill these in. So again, I'll go back to Desmos and put this function in. I get rid of this f and this f, and now we'll put in f of t equals, and then we'll put in negative 16t squared plus 256t plus 272. 16t squared plus 256t plus 272. I'll just double check to make sure that that's right. Great. All right, and so then we're doing f of 8.5 minus f of 8. So then, and again, all this is just plugging in. So again, we can do this by hand. It's f of 8. All we're doing now is just plugging in over 8.5 minus 8, negative 8. So then negative 8 would go here. And again, what's great about the technology here is that now you want to do it on 8.1. You would just then go back and you would just plug in 8.1 here. So then this is just 8.1. This is 8.1. Okay, then that's negative 1.6. And what we should be noticing here is that the closer we take this value to 8, the closer we should be getting to 1 and only one number, right? So now I think the next number is 8.01. So we go here, 8.01, 8.01, negative 0.16. Negative 0.16. Okay. Again, we think the answer should be getting closer and closer to 0. Let's put another 0 here, another 0 here, negative 0.016. And I hope we're noticing a pattern. So that's with 2 zeros, and finally with 3 zeros, negative 0.0016. Okay. All from the calculator. And so this lends us to believe that we're getting, the closer we take this value to 8, the closer the actual slope of the secant line is 0. This makes us think that the tangent line and the slope of that is 0. In other words, the instantaneous velocity is 0. What value does that occur? That occurs at the value 8. For what values t on the interval is instantaneous velocity is negative, right? So let's translate this. This means that when is the function going down? Right, and so that looks like it's from 8 to 17. Right, this is when the function's going down. Oh, they want an inequality, so you can do 8 less than t less than 17. So here's interval notation, but it looks like they want inequality notation. All right, so we talked about this in class 2. The limit is x goes to f of x exists. Does it always have to equal f of a? Not necessarily. So this is a false statement. False. The limit, if it exists, depends on values of f near a, but it does not depend on the value of f of a. Doing some limit evaluation. Use the graph of h in the given figure to find the following values, if they exist. The value of h at 3, is the black dot at 3. That is 7. What's the limit as x goes to 3? Well, as you come from the left, as x goes to 3, yes, you come from the left, it looks like it's 5. If you come from the right to above 3, it looks like it's also 5. Looks like it's 5. H of 7, the value at 7 is undefined. Let's see if that's a choice. H of 7 is undefined. We said the limit as x goes to 3 was 5. And then finally, and indeed the limit as x goes to 7 of h of x. Here's h of x. As x goes to 7, here from the left, looks like it's 1. From the right, it looks like it's still 1. 1. And then the limit as x goes to h of x of 8. That looks like that's perfectly nice. That's just 2. Another one. Let's see what this one says. Make this a little bigger. Use the graph of g in the figure to find the following values. G of 0, here's g, the blue dot for 0 is -2. The limit as x goes to 0. From the left, it looks like it's -3. From the right of 0, it looks like it's -3. The limit is -3. What's the value at 1? At 1, it looks like it's -2. And the limit as x goes to 1. From the left, here's 1. From the left, it's on this graph, so it looks like it's -2. From the right, it looks like it's -2. The limit is -2. Same thing here. We might have some new definitions. Use the graph of f of x in the given figure to find the following values, if they exist. F of 3, where's the black dot for f of 3? Let me just look at the whole graph to make sure. There it is. I was about to say it doesn't exist, but the black dot for f of 3 is here. It's -4. The black dot for 0, that's what f of 0 means. At 0, the black dot is here. It's 5. The limit as x goes to 3. From the left, if I'm rolling along this thing, from the left it looks like it's 4. From the right, it looks like it's 4. The limit is 4. The limit as x goes to 0. From the left, 0 looks like it's 5. From the right of 0, looks like it's 5. The limit is 5. So here when you're filling this in, you would just plug in 5 there. You would click A and put in 5. There's another one. F of 3. Black dot for 3, I'm sorry, in this case the blue dot for 3 is on the axis. That means the y coordinate is 0. The limit as x goes to 3. From the left, looks like it's 2. From the right, looks like it's also 2. The limit is 2, even though the value of f at 3 is 0. As x goes to 4, going to 4 from the left gives me 2. Coming to 4 from the right, looks like again it gives me 2. The limit is 2. At 5, 5 is nice. Looks like it's just going to be 1. Right? From the left, it's 1. From the right, it's 1. Looks like the limit is 1. Here we got a function and we want to look at the limit. Again, this would be something like there would be a question like this on the final where you have to do this calculation with your calculator. I will use Desmos for this one in just a moment. Let's zoom in on it. Make 2 tables, one showing the values of g for 15.9, 15.99, 15.999. So we'll put this function into Desmos. G of t is equal to, and then we'll put it in t minus 16 over the square root of t minus 4. And then you can put in square root by typing sqrt minus 4. And yeah, from this we can go ahead and make this table very nicely, table of values. And then we'll put all these numbers in. So they wanted to know 15.9, 15.99, 15.9, 15.99, and then 15.999. So it definitely looks like that the limit, as you pick these values of x, or in this case t, closer and closer to 16, it looks like the answer is 8. Well, but all these limits are from the left, right, of 16. So it looks like the limit from the left is 8. And let's see what happens on the right. Let's just make sure we're putting in these numbers right. They want 16.1. Okay, so 16.01. Let's put 001. 16.01. And then 16.1. So I just decided to put them in order. Right? So it looks like the limit is actually going to be 8. And if we go over to the graph while we're here, we go here, looks like the limit is going to be, and they plot all the points for you, and it looks like that the limit, and we can zoom in. Looks like it's getting closer and closer to 8. To 8. So we would just put all those answers into MyMathLab. We got to worry about some rounding, I think. So they want us to round to round to 4 decimal places. So just make sure we're rounding those to 4 decimal places. The conjecture is then that the limit is actually equal to 8. Another one, let's take a look at this. Great. Limits. Make that a little smaller. There we go. All right. G of 2. The black dot for 2. Oh, 2's right here. The black dot for 2 is at 4. G of 2 is 4. What happens on this graph if I come from the left of 2? That's what B is saying. If I'm on the left of 2 and I go to 2, it looks like that's 2. The limit from the left of G at 2 is 2. What's the limit from the right? Well, I'm going to be on the right-hand side of 2. That puts me on this thing. If I move from the right to 2, that puts me at 4. The limit from the right is 4. The limit from the left is 2, family. The limit from the right is 4. That means there is no limit. The answer to D is the limit does not exist because the limit from the left is not the same as the limit from the right. We talked about that in class. The black dot for 3. G of 3, the black dot is at 1. The limit from the left, I'm on this graph. I'm going to come from the left of 3. That puts me, so I want to take one of these points. That puts me here. If I go to 3, that puts me here. That number is 4. Limit from the left is 4. The limit from the right of 3, I'm on this graph. I'm getting closer to 3 from the right. That is 1. Limit from the left is 4. The limit from the right is 1. Let's just answer this now. Oh, no. They don't even ask us about 3. Great. G of 4. So first of all, that means there's no limit at 3. They don't ask us that. That means that there's no limit at 3. But they now ask us what the value of G is at 4. At 4. Here's 4. Black dot. That's this number. That number is 2. And then they ask us what the limit is as x goes to 4. Limit from the left is 2. Limit from the right, still 2. 12. Sketch a possible graph of a function that satisfies the following conditions. F of 0 is 0. The limit as x goes to 0 from the left is 3. The limit as x goes to 0 from the right is 0. Let's just go ahead and translate. This means that it goes to the point 0, 0. This thing needs to go through the origin. Great. So the origin needs to be colored in as a blue circle. And that means that this one is out and this one is out because the blue dot is not at 0, 0. This just means the blue dot has to be at 0, 0. All right. So now it's either A or B. So this means that when I get on the graph and move from the left of 0, I need to be going to 3. And when I'm on the graph and I'm moving from the right of 0, I need to be going to 0. That is this one, right? Again, from the left, I need to be going to 3. From the right, I need to be going to 0. The answer is B. Sure there's nothing else left on this page. Okay, great. Great. 13. We'll talk about continuity, but let me give you the street version. Continuity means no breaks or jumps. Between values. And so, if I'm talking about continuously between 1 and 4, then I mean every number between 1 and 4. And too often we think that we just mean 1, 2, 3, and 4. No, I mean 1, 2, 3, and 4. And I also mean 1.198, 1.2434476. I mean 3.2429324644449999666627. I want every number. If I'm saying a continuance, if I want to know the continuum from 1 to 4, I need to know every number in between, not just the whole numbers. Continuity in words just means no breaks or jumps. Say whether each of the following functions are continuous or not for all values in the domain. Justify your answer. The altitude of a skydiver t seconds after jumping from a plane. So a skydiver is going to jump from a plane, right? So they're jumping from somewhere. And the question is, if I were to draw this graph, at some point this person's going to hit the ground, safely, of course, right? We hope. And so the question is, now that we've drawn this graph, if this is a representation of it, any representation that you draw, would there be any jumps or breaks in it? And the answer would be no, right? So we would say that the function is continuous because the skydiver's altitude decreases as time increases with no breaks in between, right? They're just going to fall continuously to the ground, given nothing else happens. N of t, the number of quarters needed to park in a metered parking space for t minutes. No breaks or jumps. Now we know this definitely has some jumps in it, right? This would not be continuous because, right? So if this is time, right? If you got 1 hour, 2 hours, 3 hours, it may cost $1 for the first hour. And then if you're going to be there more than an hour, it may then cost $2. And if you're going to be there more than 2 hours, it may cost $3, right? The number of quarters you need jumps, right, after a certain period of time. This clearly has jumps to a new pay scale after a particular number of hours. And so that would not be continuous. The terminology for that is discontinuous. Not continuous means discontinuous. The function n of t is discontinuous because the number of minutes must be a whole number. No, the function n of t is discontinuous because the number of quarters must be a whole number, right? So we're talking about the range. So it's the number of quarters we're talking about. Continuity. We'll define continuity soon. The number of points scored by a baseball player after t minutes, right? So again, that's going to have jumps as well, because at some point the player might have 15 points, and then after another point they'll have 27 points. After another point they may have 35 points. Damian Lillard just scored 61 points recently in a basketball game. So here, yeah, players score runs, I guess, but they're using points. But the bottom line is, because it's a whole number, you don't hit the numbers in between the whole numbers, and so that means you're jumping from point to point. So for the same reason, the number of points scored is a whole number, and so the function is discontinuous. The three conditions for continuity, we'll talk about this in class. F is continuous at x equals a if 1. F of a exists and is defined. 2. The limit as x goes to a of f of a exists. And 3. The limit f of a is equal to the limit. Right? So it's this, and it's this. $15. Determine the points at which f, the function f to the right, has discontinuity. So if f being continuous means no breaks or jumps, then f not being continuous means that either that one of these three things is going to be violated, right? So f is defined, the limit exists. This means that the limit from the left should be equal to the limit from the right, right? And then 3, there should be no holes, that the limit as x goes to a of f of x should be equal to f of a. Let's see which ones are violated. So now, if you want to find where the discontinuities are, you just need to ask, well, wait, where are the holes and where are the jumps? So we got a problem at 1. There's a hole at 1. There's a hole at 2. And then there's a break and a hole at 3. And then that's it. So we would say 1, 2, 3. So, and then now, which ones violate the first condition? So the first condition says, yo, I need f to be continuous. I need f to be defined at the point. So is there a place where there is no black dot for one of the numbers? And that is the case for 1. 1 has no black dot for 1. At least f of 2, the black dot for 2 is 1. The black dot for 3 is also 1. But at 1, there is no black dot. This function is not defined at 1. And that violates the first condition of continuity. Which one violates the second condition? That is to say that there is no limit at one of these values. Well, the limit exists at 1. The limit from the left and the limit from the right give you 5. The limit at 2 exists. The limit from the left and the limit from the right gives you 4. It's at 3 where the limit from the left is 1. The limit from the right is 2. There is no limit for 3. 3 violates the second condition. The third condition is that, okay, you got the function is defined there, the limit exists, but for some reason we define this funky thing for the limit from the left, the limit from the right is 4, but it's not the same as the value, which is 1. And so this creates a hole, right, and a discontinuity where we define to put the black dot at the place where the limit is supposed to be, not in the place where the limit is, and that violates the third condition. None of these points are continuous, but it's number 2 that violates the third condition on the checklist. Ooh, let's do another one. And we have some terminology that we'll use. Same conditions. The function needs to be defined at a. The limit as x goes to a of f of x exists. And the limit as x goes to a of f of x needs to be equal to f of a. So f of x is discontinuous where there are breaks and holes where we got, so this is defined on 1 to 6. So we're only looking inside 1 to 6, not including the 1 and not including the 6. And the way that you know that is because of the open intervals, the parentheses, means do not include the 1 and do not include the 6. So we got a big break at 2, not continuous at 2. It's not connected over 2. There's a jump at 3 here. There's a hole at 4. So 2, 3, and 4. Oh, or where the function is discontinuous, so that goes here. Let's see which ones violate the first condition. That is to say, where is this function? Is it the case that this function isn't defined at one of these 3 values? Oh, it's not defined at 4. There's no black dot for 4. Where's the second condition not satisfied? The second condition says that somewhere this limit does not exist. And the limit does not exist at 2, right? The limit from the left, the limit from the right, right? So at 2, they're saying there's a vertical asymptote. So this thing is not going to be defined at 2, and there won't be any limits connecting at 2. There is no limit at 2. And also the limit from the left and the limit from the right for 3 are also not the same. This violates the second condition at both 2 and 3. The third condition is the limit is not equal to the value of the function. That occurs, well, that just says that the black dot is not the same as the limit. And so that occurs So note that the third condition is automatically violated if either the first or second condition is violated. So we would put in everything from the first and the second condition. So 2, 3, and 4. Right, because the limit doesn't exist for some of them. The value of the function isn't there for some of them. So it's just all of them together, 2, 3, and 4. Determine the values of f. Determine the values of a for which g is continuous from the left. So if we want it to be continuous from the left, we want the limit as x goes to 3 from the left of f of, in this case it's g, to be equal to the value g of 3. Right? So the limit as x goes to 3 from the left, well, to go from the left to 3 means you need to take values of x less than 3. So we're talking about the limit as x goes to 3 of x squared plus x. When you plug 3 in, you get 12. 3 squared plus 3, 9 plus 3, that's 12. Well, g of 3 is the value of g at 3, and that's a. So that means a is g of 3, right? But if we want this to be continuous from the left, we need a to be 12. Now, if we want g continuous from the right, we need to take the limit as x goes to 3 from the right, taking values of x that are larger than 3. We would look at this branch. And so that would be the limit as x goes to 3 from the right of negative 4x plus 7. Plugging that in, that's negative 12 plus 7. That's negative 5. And so a would have to be negative 5. Is there a value of a for which g is continuous at 3? The answer to that is no, because to make it continuous from the left, it has to be 12. To make it continuous from the right, it has to be -5. But if we want it to be continuous, it needs to be continuous. The same value needs to be on the left and on the right. It's the same as for limits. So there is no value for which g is continuous at 3 because the limit from the left is 12 and the limit from the right is -5, and they are not equal. A discontinuity is removable if you can place the blue dot and fill in the problem. Or another way of saying it is that the graph has a simple hole that can be filled. Right? So an example would be this. If I had a graph that looked like, let's use a different color, that looked like this, like that, right? So if this is 3, right? So this is not continuous because the value of the function at 3 and the limit, so this is 2 and this is 7, and this function's f. In this case, f of 3 would be 7. The limit as x goes to 3 is 2. This would not be continuous because the value, the limit as you go to 3 is not the same as the value of the function. But this is not continuous. This is discontinuous at 3. But we would call this this one is a removable discontinuity because theoretically we could just, if we move this point here and filled it in, then it would be fine, right? It's just that that there's a hole in the place that we could fill in and make it okay. This one is not fixable, right? Because when you have a break, you can move this down here and fill this hole in. That does not fix the problem. So you cannot make this continuous by redefining the value of the function at -3. Classify the discontinuities in the function below. So an infinite discontinuity is like the one we saw earlier. It's like, let's see, where did it go? I thought it was this one is an infinite discontinuity too, where the graph just gets higher and higher, goes up forever. So infinite discontinuities occur at vertical asymptotes. And so what we're going to do here is take a look at this one. And so infinite discontinuities occur at vertical asymptotes. Or in other words, when the denominator is 0. When the simplified denominator is 0. I say simplify because that's the crucial point here, right? Because they want you to check x equals 2. And a lot of people are going to say that this is an infinite discontinuity because it makes the denominator 0. But you can factor this and you actually do cancel out the issue so that you aren't really dividing by 0, right? So this is x minus 7, x minus 2. You can factor that over x minus 2's. And the x minus 2's cancel. You get x minus 7. So the 2 really isn't that big of a deal. It's still not defined at 2. But now we could define it at 2 to make this work, to make this continuous. So this one is definitely removable. And the question is, what could we make it in order to define it well? And in order to find out what that would be, you would plug in the 2 into this. 2 minus 7 is negative 5. That would make it fine. Right? So factor, simplify, and then you'll see how you should define the function by plugging in the 2 into the simplified version, and then that will make it continuous. Did I skip 20? Oh, there's 20. 20's here. Same question here. I've got, let me zoom in. We've got x cubed minus 4x squared plus 4x all over x times x minus 9. We can factor out an x in the numerator. That leaves x squared minus 4x plus 4. I can factor that too. I don't really need to because it's not going to cancel out this x minus 9, but I'll do it anyway. So then this is x times x minus 2 squared, actually, all over x times x minus 9. And so the denominator is 0 when x is 0 and when x is 9. And so the function has, at 0, because you can cancel out, I'll use a different color. Because you can cancel out the x, let's use a different color. Because you can cancel out these x's, that means that we have a removable discontinuity at 0. And 9 cannot be canceled. It makes the denominator 0. That means you're going to have a vertical asymptote, and that means that's an infinite discontinuity. The closer you bring x to 9, the more this thing goes to infinity or negative infinity. (21) The intermediate value theorem says that if f is continuous, then f has to hit all the values between its max and min. So if I told you if I had a function that started here and it ended here, so and now if I draw a continuous function now to connect these 2 points, that means that I should be able to draw it. If there are no jumps or breaks, I should be able to draw it without taking my marker off the board. Well, what does that mean? That means that every y value between the minimum and the maximum actually gets hit by the function. There's some value down here that gets associated with each one of these. Okay? And so now it says use the intermediate value theorem to show that the following equation has a solution. So how would I know that the function f of x equal to 2x plus e to the 3x actually is 0 somewhere on the interval -1 to 0? So first of all, 2x and e to the 3x are continuous functions. For every x. So they're continuous. Let's find the value of the function at the left endpoint. We may need to round to 3 decimal places, so we need, they want us to do f of -1. F of -1 is 2 times -1 plus e to the -3rd. Let's see how this calculator rolls here. Do some e here. Oh, I'm not sure if they're going to make us do that. I think we should use Desmos. 2 times -1, so that's -2 plus e to the -3. Negative 1.950, round to 3 decimal places. Negative 1.950. The value at the right endpoint is 0. The right endpoint is 0, so it's 2 times 0 plus e to the 0. That's 0 plus 1, 1. So now we got a function. We don't know that much about it, but I know at negative 1, it's about negative 1.95. At 0, it's 1, and I know that if I were to draw this function from that, the function starts off negative and then ends up positive and it's continuous, then it has to hit every number between negative 1.95 and 1. It has to hit every number between that negative number and that positive number. Well, we know what number is between negative 1.95 and 1. It's 0. 0 is between these two numbers. And so by the intermediate value theorem, there must be a place in between negative 1 and 0 where this function actually hits the x-axis where it's 0. Why can the intermediate value theorem be used to show that the function has a solution on negative 1 to 0? It can be used because this is continuous and the function is defined at negative 1 and 0. Okay, it can be used because this is defined on this and that's close. It can be used because that function is defined. It can be used because this function is continuous on negative 1 and 0, and 0 is between f of negative 1 and f of 0. Because it has to hit every value between one of the values and the other of the values. Oh, we can try and guess where this is. We'll use a graphing utility. So we'll go back to Desmos, 2x plus e to the 3x. Let's take a look here. Two x plus e to the 3x. That will bring this home. Oh, and then we could do negative 1 to 0, but it's here, right? Negative 0.242. Three decimal places. And looking at the picture, I guess we can zoom in to see what it looks like. Okay, let's see what picture this matches. Looks like it matches D. Just double check. Yep. All right. Let's see here. $17. What else we got here? All right. Hope that helps.